somewhere in your home, there's a piece of paper with your address on it. Every line of it is true, and every line of it is unfinished. A house number, a street, a town, a region, a country. Most addresses stop there because no letter has ever needed more. But the lines keep going. After the country comes a planet. After the planet, a star. And after the star, the lines turn strange because they name places almost nobody can point to: a spiral arm, a galaxy, a small cluster of galaxies, and then something so large it was only discovered and named within living memory. School children sometimes write the long version in the front of a notebook, half as a joke: name, street, city, country, Earth, the solar system, the Milky Way, the universe. The joke is truer than it looks. Those are real lines of a real address. What almost nobody is ever taught is what the last few lines actually mean. What the Milky Way is, how we found out, what it belongs to, and how far the writing goes before it must stop. Here is what this hour is for. We're going to write out the rest of your address, one line at a time. Each line is a real place with a real shape and a real history. And some of those histories were settled within the last 100 years by people arguing in museum auditoriums and staring at photographic plates. By the end, you will know every line. And one of them, the nearest island beyond our own, you will be able to step outside and find with your naked eye tonight. Before we begin, one small request. If these long, unhurried hours in the universe are something you enjoy, please take a second to press like and to subscribe. It costs you nothing, but it tells us to keep making documentaries like this one, and it helps other people who love the night sky find their way here. Thank you. And thank you for spending this hour among the galaxies. The first unfamiliar line of your address is the oldest one. People were naming it thousands of years before anyone knew what it was. And almost every name they gave it was about the same thing: milk. Go somewhere truly dark on a clear, moonless night and let your eyes adjust for 20 minutes. A band of pale light appears, arching from one horizon to the other. It does not twinkle. It does not move against the stars. It simply hangs there, like smoke that never drifts. The ancient Greeks called it galaxies, kyklos, the milky circle, and our word galaxy still carries their milk inside it. The Romans called it the Via Lactea, the road of milk. In China, it was the Silver River. Cultures that never met agreed on the essentials. It looked poured, spilled, flowing. A river of something faint, running through the middle of the sky. Look closely on the best nights, and the river even has features. Along one long stretch, the band splits in two, divided by a dark channel that old star atlases call the Great Rift, as if the river forked around an island of nothing. Remember that darkness. It is not an absence, and it will matter more than once before we are done. For most of human history, that was all anyone could say. The band was aglow, and glows keep their secrets. A few thinkers guessed better than they could know. The Greek philosopher Democritus, 24 centuries ago, suggested the milky glow might be nothing but stars, multitudes of faint stars, too small and too crowded for the eye to separate. It was a beautiful guess. It was also unprovable, and it stayed unprovable for 2,000 years, waiting for a piece of curved glass. Then, in the winter of 1610, in Padua, a mathematics professor named Galileo Galilei points a new instrument at the band. He has already used his telescope on the moon and found mountains. Now he turns it to the Milky River, and the milk dissolves. Everywhere he looks, the glow breaks apart into stars. Not dozens, not hundreds. In his little book published that spring, he writes that the galaxy is nothing but a congeries of innumerable stars, heaped together, so many that the eye, unaided, blurs them into cloud. The river of milk is a river of suns. That answer, magnificent as it was, only deepened the question. Because the stars of the band are not spread evenly across the sky. They crowd into that one great circle. And there's only one arrangement that can explain it. If you stand inside a flat disk of stars and look along the flat, you see star behind star behind star, piled into a bright band. Look up, out of the disk, and the stars thin quickly to black. The Milky Way is not a river in the sky. It is an entire disk of stars, seen edge-on from the inside, which raises the problem that would occupy astronomy for 3 centuries. We live inside the thing we're trying to see. Nobody can step outside it to look. Mapping our galaxy is like mapping a forest you can never leave by measuring the trees. So what did the mapping find? What is the shape of the forest? The first person to seriously attempt the map was William Herschel, the great telescope builder, in 1785. His method was heroic in its simplicity. If you cannot leave the forest, count the trees. He divided the sky into hundreds of small patches and, with his sister Caroline recording at his side, counted the stars in each one, reasoning that where the counts ran deep, the galaxy must extend far. The result was the first map of the Milky Way ever drawn, a flattened, splintered disk of stars, with the sun close to the middle. It was a beautiful map, and it was wrong in the one way that mattered, through no fault of his. Herschel could not have known that the space between the stars is not clear. It is faintly hazed with dust, the same dust that carves the Great Rift, and the haze swallows starlight long before the eye runs out of stars. Herschel was not measuring the forest. He was measuring how far he could see into the fog, which is the same in every direction. That is why he found himself in the center. The galaxy hides its true shape from everyone inside it, and it would keep hiding it for over a century more. Here, then, is the real map, assembled since, from star counts and radio surveys that pierce the dust, and from the hard-won correction to Herschel's fog. The Milky Way is a barred spiral galaxy, a flat, slowly turning disk of stars, about 100,000 light-years across. Through the middle runs a bar of older, golden stars, and for the ends of the bar the spiral arms unwind, 2 dominant ones, which astronomers call scutum, Centaurus and Perseus, plus lesser arms and spurs between them, all bright with young blue stars strung along their lengths like lamps on a wire. At the very center sits a dense bulge of stars, and, buried inside it, a supermassive black hole 4 million times the mass of the Sun. A monster with its own story, quiet for now, and not our destination tonight. It is fair to ask how anyone can know this from the inside of the thing being described. The answer is that the fog is not equally thick for every kind of light. Infrared light, heat light, with waves too long for the eye, slips through the dust that defeated Herschel. When infrared surveys counted millions of giant stars toward the galaxy's heart, the counts came back lopsided. On one side of the center, the stars stood measurably nearer and more crowded than on the other. Only one shape does that, a bar, seen at an angle, one end leaning toward us. We never did leave the forest. We learned to see through the fog instead. For all its breadth, the disk is astonishingly thin, roughly 1,000 light-years top to bottom, 100 times wider than it is thick. Those are the proportions of an old compact disk, a shining, grooved platter, impossibly wide for its thinness, turning in the dark. How many stars ride that platter? Here astronomers are honest. Nobody has counted, and nobody can. The faintest stars, the red dwarfs, are so dim that we cannot see most of them even a short distance away. So the total is an estimate, somewhere between 100 billion and 400 billion stars. The uncertainty is itself the lesson. We are missing most of our own galaxy's population from the inside. And where are we? Not at the center. Not even close. The sun rides in a minor arm, a spur, really, called the Orion Arm, about 26,000 light-years out from the middle, roughly halfway between the center and the rim. A side road between 2 great avenues. Numbers this size slide off the mind. So let us build something we can hold, and we will keep it for the rest of the hour. Shrink the Milky Way until it fits on the Earth, until the whole 100,000 light-year disk is the width of a continent, for 1,000 kilometers coast to coast. On that continent, how big is the sun? Not a city, not a building. On the continent-wide galaxy, the sun is 6,000ths of a millimeter across, the size of a single red blood cell. The entire solar system, everything the planets enclose, is a coin lying somewhere in the interior. And the nearest other star to us, with its own microscopic worlds, is another blood cell, 2 city blocks away. That is a galaxy, a continent of near-perfect emptiness, salted with a few 100 billion microscopic points of fire, each one blocked from its neighbors, all of it turning. Because the map is still, and the real thing is not. Every star you have ever seen is moving. The whole disk turns, not rigidly, like a wheel, but star by star, each on its own orbit around the distant center. The Sun is no exception. Right now, is carrying you around the galaxy at about 230 kilometers every second, 500,000 miles an hour. The spiral arms, strangely, do not turn with the stars. In the leading model, an arm is not a fixed formation of particular stars at all. It is a slow-moving zone of congestion, a traffic jam in the disk. Stars drift into the jam, crowd, linger, and pass through, and while the gas is compressed inside it, new bright stars flare there. The jam itself creeps around the galaxy far more slowly than the traffic. The arms you see in every photograph of a spiral galaxy are not objects. They are events permanently in progress, made of different stars every time you look. The Sun's own path has one more quiet flourish. As it circles, it also bobs, rising slowly up through the thin disk, slowing, drifting back down through the midplane and below, once every several tens of millions of years like a horse on an unhurried carousel. Nothing about the ride is felt on Earth. It is simply what orbiting a galaxy is like from the inside. And yet the circle is so large that at that speed, one lap, one orbit of the galactic center, takes somewhere between 225 and 250 million years. Astronomers call it a galactic year. It is the longest year you belong to. Count the Sun's laps. Our star is about 4.5 billion years old, and one lap takes roughly 250 million. So in its entire existence, from before the Earth had a solid surface to this morning, the Sun has circled the galaxy about 20 times. 20 galactic birthdays. The Sun is, by its own calendar, barely out of childhood. Run it the other way. 1 galactic year ago, the Sun was last in the part of its orbit it occupies tonight. On Earth, the continents were fused into one, and the very first dinosaurs were small, quick, and new. The entire age of dinosaurs, their rise and their reign and their ending, fits inside a single lap of the Sun. And humanity? All of recorded history, every city, every voyage, every name ever written down, has lasted 5,000 years. In that whole time, the Sun has moved less than 4 light years along its orbit. On the galactic circle, less than the distance to the next star over. The galaxy has not had time to notice us. We arrived mid-stride, in the middle of a step it began before our species existed and will finish long after. For almost all of human history, this wheel of stars was assumed to be everything. The word universe and the word galaxy meant the same thing, because what else could there be? The little glowing smudges telescopes kept finding between the stars, spiral-shaped, faint, uncounted, were assumed to be clouds of gas inside the one great system. Whether anything at all lay beyond the Milky Way was not a debate. Then, a little over a century ago, it suddenly was. And the argument came to a head on a single spring evening in a museum auditorium in Washington, D.C. It is the evening of the 26th of April, 1920, in the Baird Auditorium of the Smithsonian's Natural History Museum. 2 astronomers are here to argue, politely and in public, about the size of everything. Arguing for one view is Harlow Shapley of Mount Wilson Observatory. Young, ambitious, raised on a Missouri farm, a former newspaper crime reporter who liked to say he had chosen astronomy from the front of the course catalog because he could not pronounce archaeology. Shapley has spent years measuring the great globular clusters, dense balls of ancient stars that swarm around the galaxy, and they have told him 2 enormous things. First, the Milky Way is far larger than anyone had believed. Second, the Sun is nowhere near its center. On both counts, history will prove him right. But Shapley pushes further. A galaxy that large, he argues, must be the whole show. The faint spiral smudges are minor whirlpools of gas inside it, or just beyond its rim. One system, one island, nothing else. Opposite him stands Heber Curtis of Lick Observatory. Older, precise, a former professor of Latin and Greek who came to astronomy late and mastered it. Curtis looks at the same spirals and reads them completely differently. Their light looks like the pooled light of countless stars. New stars flare in them, the way novae flare among our own. They are not details inside our galaxy, he argues. They are other galaxies, separate systems of stars, staggeringly far away, each one comparable to the entire Milky Way. Other islands, in a dark ocean nobody had imagined. The idea itself was old. The philosopher Immanuel Kant had reasoned his way to it in the 1750s, and it had since acquired an unforgettable name: island universes. So the question on the table that evening could not have been larger. Is the Milky Way the universe? Or is it one of a multitude? Feel the difference between those two answers for a moment, because everything that follows depends on it. In Shapley's universe, our galaxy is the single continent of stars, and beyond its shores lies only thinning emptiness forever. In Curtis's universe, the night sky is an archipelago without end. Every faint spiral another 100 billion suns, another possible history, another galaxy's worth of worlds. Two visions of reality, differing by a factor of billions, and in 1920 the human race genuinely did not know which one it lived in. The audience goes home without an answer, because in 1920 there's no way to decide. Both men can be eloquent, neither can be sure. Everything hangs on a single missing number, the distance to just one spiral. If a spiral could be shown to lie beyond the Milky Way's edge, Curtis wins, and the universe expands a millionfold in an evening. But distance is the one thing a telescope does not show you. A faint patch of light might be a small cloud nearby, or a vast city of stars very far away. To tell which, astronomy needed a measuring stick that could reach across the dark. Here is the strange part. The measuring stick already existed. It had been discovered years before the debate, in Massachusetts, by a woman who was paid 30 cents an hour, and whose name most of the audience that evening would not have known. Her name was Henrietta Swan Leavitt. She worked at the Harvard College Observatory as a computer. The era is word for the women employed to measure and catalog the stars captured on the observatory's glass photographic plates. The work was meticulous, repetitive, poorly paid, and close to advancement. Women computers were not permitted to use the great telescopes whose plates they analyzed. Leavitt, who had lost most of her hearing in adulthood, was assigned to the variable stars, stars whose brightness slowly pulses, dimming and brightening over days or weeks. She was very good at the work. Over her career, she discovered some 2,400 variable stars, roughly half of all those known in her lifetime. And in the plates of one small neighboring star cloud, she found hundreds of a particular kind, called Cepheids. In 1908, she noticed something no one had ever noticed. The brighter ones seemed to pulse more slowly. By 1912, she had made it exact. A Cepheid's rhythm tells you its true brightness. Slow pulse, brilliant star. Quick pulse, fainter star. Every time, in lockstep. It takes a moment to see why that unlocks the universe. Watch any Cepheid, anywhere, count the days of its pulse, and Leavitt's law tells you how bright it truly is. Compare that with how bright it appears from Earth, and the dimming gives away the distance. The way you could judge the distance to a lighthouse if you knew the wattage of its lamp. A Cepheid is a lighthouse with its wattage written in its rhythm. Astronomy finally had its yardstick. All anyone had to do was find a Cepheid in a spiral nebula. That is much harder than it sounds. If the spirals really were island universes, then even their brightest stars would appear almost impossibly faint, single grains of light lost in the general glow. Resolving one, and then catching it in the act of pulsing, would demand the most powerful telescope on Earth, pointed at the same object night after night by someone stubborn enough to compare every plate against every other. The instrument equal to the task sat on Mount Wilson in California. The Hooker telescope, its mirror 100 inches across, the largest in the world. And in the autumn of 1923, a young astronomer there, a Missouri-born scholar named Edwin Hubble, who had studied law before choosing the sky, was photographing the Great Spiral in Andromeda, the largest and most famous smudge in the sky. On the night of the 5th of October, 1923, Hubble takes a plate of the nebula and finds a new point of light in one of its arms. He marks it in for nova, an exploding star, interesting but routine. Then he does the careful thing. He pulls the archive of earlier plates of that same arm and compares night against night, year against year. The point of light is not new at all. It has been there all along, brightening and dimming on a steady rhythm of 31 days. It is not a nova. It is a Cepheid, a lighthouse, standing in Andromeda itself. On the plate, Hubble crosses out the N and writes 3 letters and an exclamation mark. In red, VAR. That small red word may be the largest correction ever written, because Leavitt's law now did the rest. 31 days of pulse meant star of tremendous true brightness. And Andromeda's lighthouse appeared so faint that it had to stand about 1,000,000 light-years away, far beyond the rim of even Shapley's enormous Milky Way, far beyond everything. Not a whirlpool inside our galaxy. Not anywhere near our galaxy. The debate was over, settled not by eloquence but by a smudge of silver grains on glass. Hubble wrote to Shapley with the news. Shapley, the man who had argued that the Milky Way was everything, read the letter, held it out to a student in his office, and said, "Here is the letter that has destroyed my universe." To his lasting credit, he accepted the verdict. The measurement was simply right. When the result was formally announced, at a scientific meeting on the first day of 1925, astronomy's map of reality changed size by more than any map has changed before or since. Andromeda was an island universe. And if that one spiral was a galaxy in its own right, so were the others, the thousands of fainter spirals already photographed, and the billions beyond them. Today's estimate, and it is an estimate, is that the observable universe holds hundreds of billions of galaxies, perhaps as many as 2 trillion, hundreds of galaxies for every human being alive. Leavitt did not live to see it. She had died in 1921, at 53, still a computer. 4 years later, a member of the Royal Swedish Academy of Sciences wrote to her, beginning the paperwork to nominate her for the Nobel Prize, not knowing she was gone. The prize is never awarded posthumously. The ruler she built now reaches across the universe. As for the island that settled everything, it has not gone anywhere. It is above your roof right now. And of all the galaxies in the sky, this is the one you can find with nothing but your own eyes. On a clear, dark autumn night, away from city lights, find the constellation Cassiopeia, the bright, unmistakable W of 5 stars. The deeper half of the W works as an arrowhead, and it points the way. Follow it down, about a fist and a half at arm's length, into the quieter stars of the constellation Andromeda, and let your eyes settle. There, faint, elongated, easy to miss, and impossible to unsee, is a small gray smudge of light. It does not look like much. It looks like a thumbprint on the sky. That thumbprint is the Andromeda galaxy, a spiral like ours, but larger, perhaps 1 trillion stars, 2.5 million light-years away. It is the most distant thing a human eye can see unaided. Everything else in your night sky, every star, every planet, the Milky Way band itself, is local. That one smudge is another island entirely. It is also the closest thing our galaxy has to a mirror. We can never photograph the Milky Way from outside. Every portrait of our own galaxy you have ever seen is an artist's reconstruction, but Andromeda is a galaxy of the same family, seen whole from without. When you look at that smudge, you're looking at approximately what we look like, and the view goes both ways. From a world in Andromeda, our Milky Way hangs in their sky as a faint, elongated thumbprint of exactly the same kind, and any eyes there that see it are seeing the combined light of every star around us, ours included, blurred into a glow. And it is a time machine. The light entering your eye left Andromeda 2.5 million years ago. When it set out, there were no human beings. Our ancestors in Africa were just beginning to chip stones into the first crude tools. Every step from there to you, fire, language, cities, telescopes, happened while that light was crossing the gap. You're not seeing Andromeda as it is. You're seeing it as it was before our species existed, at the far end of the longest unobstructed view your eyes will ever have. Put on our model. Shrink the Milky Way to a continent again, 4,000 kilometers wide, with the sun a red blood cell somewhere in its interior. Where's Andromeda? It is another continent, wider than ours, floating 100,000 kilometers away, a quarter of the distance to the moon. Two continents of stars, adrift in a dark room, with almost nothing in between. But the room is not static. In the light of Andromeda, there is one more message, and it took a spectroscope to read it. Starlight carries a fingerprint of lines, and when a source moves away from you, the lines stretch toward the red. Nearly every galaxy in the sky is redshifted, receding, carried off by the expansion of the universe. Andromeda is not. Its lines are compressed, shifted toward the blue. Andromeda is one of the very few galaxies in all the sky that is moving toward us, closing the gap at about 110 kilometers every second. 250,000 miles an hour. It is not passing by. It is coming here. Say that carefully, because it sounds like a threat, and it is not one. It is an appointment, and an extraordinarily distant one. In the long-standing forecast, the Milky Way and Andromeda meet in around 4 to 4.5 billion years. The sun will still exist, though it will be old by then, swollen and brightening at the end of its steady middle age. For a billion years is as far from us as the origin of life on Earth, but in the other direction. Nothing about this appointment concerns you, your descendants, or anything you would recognize as the future. What earns it a place in this story is what it reveals about what galaxies are. Even the geometry is still being refined. Measurements from the Gaia Space Observatory, which tracked Andromeda's sideways drift with exquisite care, suggest the first pass may be more glancing than head-on, nudging the schedule later. And the newest analyses, which fold in the gravitational tug of the neighboring galaxies, go further. In roughly half their simulated futures, that first pass is wide enough that the merger slips past 10 billion years, or never quite happens at all. So the honest summary is this. The two galaxies are falling toward each other now. The physics of what happens when galaxies meet is not in doubt, and the appointment is written in pencil, the date, and even the meeting itself. Now, what does a collision of galaxies actually look like? Here is where every instinct fails, because the word collision belongs to a world of solid things, and a galaxy is barely there at all. Remember the continent. A few 100 billion red blood cells, each one blocks from its neighbors. When two galaxies meet, one nearly empty continent glides into another. The models are blunt about the consequence. As the two systems sweep through each other, star finding star, almost no two stars will ever actually touch. The gaps are simply too wide. Trillions of suns will interleave like two swarms of fireflies drifting through one another in the dark. But the galaxies do not pass through unchanged, because stars are not all a galaxy carries. Between the stars lies gas, thin, cold, and vast, and the gas cannot interleave. Gas meets gas and slams, compresses, and lights up. The meeting will ignite brilliant bursts of new stars along the collision fronts, hot, blue, and short-lived, like sparks off a grindstone. Gravity does the slower work. On the first pass, the two spirals will swing wide, trailing streamers of stars behind them. Then they fall back, pass again and again, each pass blurring them further, until, over 1 billion years or more, the two great spirals settle into a single, calm, oval galaxy, an elliptical, golden with age. Astronomers, who name things centuries early, already call it Milkomeda. None of that choreography is guesswork, because the sky is full of other couples caught mid-meeting. Telescopes have photographed colliding galaxies at every stage. pairs just beginning to lean toward each other across a bridge of stars. Pairs like the famous antennae galaxies, two tangled spirals flinging long tails of stars into the dark while new suns flare along their seam. And old, settled ellipticals still wearing faint shells and ripples, the last slow echoes of a meeting finished long ago. No one will watch our merger from beginning to end. But laid side by side, the sky's other collisions become a flipbook of the whole event. Every page a different pair, together telling one story. And the sun? In most simulations of the merger, it survives untouched. Collisions between stars are that rare. But it is likely to be carried outward, swapped onto a wide new orbit far from its old side road. If anyone is standing on a world near the sun on that far evening, they will look up at a sky no human has ever seen. Two wrecked spirals braided together, arcs of newborn blue, and the combined glow of a trillion elderly suns. The show, in fact, begins long before the meeting. Over the coming billions of years, that faint thumbprint in the autumn sky will slowly grow, wider, brighter, unmistakable, until Andromeda hangs across the night as a vast, tilted wheel of light, larger than any constellation, its dust lanes visible to whatever eyes are watching. The nearest island will become, by the end, half the sky. Two galaxies do not collide the way ships do. They merge the way rivers do. And the meeting is not an ambush between strangers. The Milky Way and Andromeda have been bound to each other since before the sun existed, the two great anchors of the same small neighborhood. Because your address does not stop at the galaxy. The next line has a name, too. Astronomers call it the local group, and the modesty of the name is almost funny. It is a gathering of galaxies. More than 50 found so far, with faint new members still turning up, bound to one another by gravity across a region some 10 million light-years wide, while the wider universe stretches and carries distant galaxies apart. The local group holds together. These galaxies are not drifting past one another. They are family, and they're staying. Two members outweigh all the rest combined. Andromeda and the Milky Way, the group's twin anchors, orbiting their common center in the long, slow fall that may yet end in Milkomeda. Third place goes to Triangulum, a lovely, loose spiral of perhaps 40 billion stars, keeping close company with Andromeda. And after those three, the roll call changes character completely. Every other member is a dwarf. Small galaxies of a few billion stars, or a few hundred million, or fewer. Faint sprays and smears of stars, some so dim they were only discovered in recent decades. This is worth pausing on, because it corrects the picture the posters give us. The great spirals are the exceptions. The most common kind of galaxy in the universe is small, faint, and nameless. For every continent, there are dozens of scattered villages. The faintest of these dwarfs hold a secret worth planting here. When astronomers clock the speeds of their few stars, the stars move far too fast for the feeble gravity of what is visible. In the most extreme cases, measurements suggest the visible stars are outweighed hundreds of times over by something that cannot be seen. File that away. It is the second quiet hint that the universe is mostly hidden, and before the hour ends, the hint becomes the headline. Two of those villages you can see with your naked eye if you stand on the right half of the Earth. From the southern hemisphere, on dark nights, two soft, glowing patches hang away from the Milky Way band, like torn-off pieces of it. Southern peoples knew them and told stories about them for thousands of years before any European saw them. The name that stuck came from the cruise of Magellan's voyage in the 1520s, and they are still called the Magellanic Clouds. They are dwarf galaxies, satellites of our own, roughly 160 and 200,000 light-years away, slowly wheeling around the Milky Way as the moon wheels around the Earth. They will not wheel forever. Models suggest that the larger of the two is falling inward, and that in around 2.5 billion years, the Milky Way will draw it in entirely. A rehearsal on a smaller stage for the greater merger that may follow. Set the whole family on our model. The Milky Way is a continent. Andromeda is a second continent a quarter of the way to the moon, an entire local group. Every spiral, every dwarf, all 50-plus members, fits inside a sphere about as wide as the real distance from the Earth to the Moon. One lunar gap, holding every galaxy that will ever be truly ours. 50 islands, great and small, bound in one small province of the universe, which finally forces the deepest question of the hour. Where do they come from? Nobody has ever watched a galaxy being born. To explain these 50, astronomy had to reconstruct events from a time before the universe contained a single star, a time when there was nothing to see at all. Begin with the universe as it was in its infancy. No stars, no galaxies, no light sources of any kind. Just hot gas, thinning and cooling as space expanded, and spread with an evenness that should be impossible. Everywhere astronomers look in the universe's earliest light, the gas differs from place to place by about 1 part in 100,000. Pour a lake that level, and no shore on Earth could match it. 1 part in 100,000. Those faint ripples, regions a whisper denser than their surroundings, are the seeds of everything. Because a place with slightly more matter pulls slightly harder and gathers more, and pulls harder still. Gravity is patient, and it plays favorites forever. But here the story takes a strange and modern turn, because in the current understanding, the first things to gather were not made of ordinary matter at all. Threaded through the young universe was a second kind of matter, invisible, silent, passing through ordinary matter like a draft through a screen door, and there was far more of it than of everything we can see. Astronomers call it dark matter. What it actually is, nobody yet knows. Hold on to that, because it returns before this hour ends. What it did is written across the sky. Its gravity gathered first, pooling into vast, unseen clumps, halos, while the ordinary gas was still too hot and hairy to settle. The halos became the molds. Ordinary gas fell into their gravity, cooled, and pooled at their centers. Astronomers call the era before anything ignited the cosmic dark ages, and they mean it literally. Hundreds of millions of years in which the universe was transparent, full of matter, and completely unlit, like a theater after the house lights fail. Then, in the current understanding, a few 100 million years after the beginning, the pooled gas finally crushed itself into the first stars, and light returned, first as scattered points, then as crowds of them. The first galaxies were small, dwarfs, villages of stars, scattered by the billion. Then the villages began to merge. This is the part astronomers are most confident of, because the evidence is everywhere. Galaxies grow from the bottom up. Small ones merge into larger ones. The larger ones swallow more villages and each other. And over 13 billion years, the hierarchy builds continents. Our own galaxy is such a construction. The oldest stars in the Milky Way are close to 13 billion years old. The ages carry real uncertainty, but they are among the oldest objects known, and those ancient stars are the surviving citizens of the little galaxies that merged long ago to found ours. Honesty requires one more paragraph, because this story's first chapter is being rewritten right now. When the James Webb Space Telescope opened its eye in 2022, it looked further back in time than any instrument before it, and found early galaxies that appear brighter, bigger, and more settled than the models expected, sooner than expected. Headlines shouted about broken cosmology. The working truth is calmer. The framework of ripples, halos, and mergers still stands on a mountain of evidence. But the first galaxies seem to have assembled faster than we thought, and nobody is yet sure why. The candidate explanations are being weighed as you listen. Perhaps the earliest galaxies turned their gas into stars far more efficiently than galaxies manage today. Perhaps the first generations of stars burned unusually bright for their mass. Perhaps some of the light is being misread. Each possibility would leave its own fingerprint in the data, and the telescope is still collecting. It is an open puzzle under active study, which is science operating exactly as designed. The frontier is supposed to be unfinished. But notice what the bottom-up story quietly implies. If great galaxies are built by absorbing small ones, the building should never really stop. There should be evidence of recent meals. There should, perhaps, be a meal in progress. There is. Our galaxy is eating another galaxy right now. On the far side of the Milky Way's core, hidden from us behind the crowded star fields of the bulge, there is a dwarf galaxy in the last age of its existence. It is called the Sagittarius Dwarf, and it was only discovered in 1994 precisely because it hides behind the thickest part of our own galaxy. Astronomers found it the way you might notice a stranger in a packed crowd, by realizing a whole cluster of faces was subtly the wrong color and moving together. The Sagittarius Dwarf is falling through the Milky Way. It has been falling for billions of years, looping through the disk again and again, and on every pass our galaxy's gravity strips stars from it the way wind strips leaves. The stolen stars do not scatter randomly. They trail along the dwarf's orbit, ahead of it and behind it, stretched into an immense, faint ribbon that by now wraps the entire sky. Astronomers call it the Sagittarius Stream, a river of stars flowing around the whole galaxy, marking the orbit of a dying companion. There is no explosion in this story, no wreckage. The dwarf stars are not destroyed, they are adopted. One by one, they stop belonging to the Sagittarius Dwarf and start belonging to the Milky Way, keeping only their motion as a memory of home. In a few billion years, the dwarf will be gone entirely, and its citizens will simply be our stars, indistinguishable in the census except to instruments precise enough to read their old allegiance in their orbits. And the Sagittarius Stream is not alone. When the Gaia Observatory measured the positions and motions of nearly 2 billion stars, one star charted for every 4 people alive, astronomers combing its catalog found the sky threaded with dozens of such streams, thin rivers of stars on shared orbits, each one the remains of a dwarf galaxy or a star cluster consumed long ago. Some of the meals were ancient. Deep in the galaxy's inner regions lies a vast shoal of stars from a galaxy swallowed some 10 billion years ago, in the largest merger our galaxy is known to have undergone. The Milky Way's calm disk turns out to be built over a deep archaeology of Eden. This is what a galaxy is seen clearly, not a fixed object but a long appetite, ancient and still feeding. The word cannibalism sounds violent, but watch the actual process and it is closer to confluence, tributaries joining a river, over spans of time in which 1 billion years is a season. Every stream in the sky is also something else, a measurement. A stream of stars traces the gravity it moves through, the way a ribbon dropped in a current traces the water. And when astronomers use the streams and the orbits and the motions of everything our galaxy holds to weigh the Milky Way, to finally put a number on our own home, the number came back wrong. Not slightly wrong. Wrong by a factor of 5 or more. Nearly everything the Milky Way weighs is something no telescope has ever seen. The trail to that discovery begins with a prediction so ordinary it was barely worth stating. Galaxies spin, and anything orbiting a central mass should obey the rule the solar system has followed forever. The farther out you are, the slower you go. Mercury tears around the sun, distant Neptune ambles. It has to be so because gravity weakens with distance. Plot orbital speed against distance, and the line must fall. Every textbook said a galaxy's stars would do the same. Fast near the bright, crowded center, slower and slower out toward the dark rim. In the 1970s, an astronomer named Vera Rubin set out to measure it. She had spent a career being told no. Her chosen graduate school did not admit women. The great observatories for years did not admit women observers. She became the first woman formally granted time on the famous telescopes of Palomar Mountain in 1965, well into her working life. She chose galaxy rotation partly because it was quiet, a solid, unglamorous problem out of the way of the fights over the fashionable topics. It turned out to be a trapdoor into the deepest problem in physics. Working with Kent Ford, who had built one of the most sensitive spectrographs of the era, Rubin recorded the rotation of the great spiral next door, Andromeda, point by point, from its blazing core out to its faint edges. Ford's instrument could read the speed of a smear of starlight too dim for earlier machines. The measurements were clean and repeatable. and they made no sense. The curve refused to fall. Stars at Andromeda's far rim were orbiting essentially as fast as stars near its center, as if Neptune moved at the speed of Mercury. Rubin and Ford went on to other spirals, one after another, and the answer would not change. Flat curves, galaxy after galaxy after galaxy. The rule that governs the solar system simply fails at the rim of a galaxy. There are only two ways out. Either the law of gravity itself breaks down at galactic distances, and that idea has been explored seriously and never made to fit all the evidence, or every one of those galaxies contains far more matter than it shows. Run the numbers on the second answer, and the requirement is astonishing. To hold those speeding rim stars in their orbits, each galaxy must sit inside an enormous sphere of unseen mass, a halo, wide and deep, outweighing the visible stars, gas, and dust roughly 5 or 6 times over. The glowing spiral, it turns out, is not the galaxy. It is the bright sediment settled at the center of something far larger that we cannot see at all. The halos that built the galaxies in the beginning never left. They're still here, still holding everything together, and still invisible. Rubin was not the first to glimpse this. In 1933, a brilliant, abrasive Swiss astronomer named Fritz Zwicky had clocked the galaxies of the Coma cluster racing far too fast for the visible matter to hold, and coined a name for what must be missing: Dunkelmaterie, dark matter. His colleagues found the man difficult and the claim outlandish, and the idea sat ignored for 40 years, until Rubin and Ford's flat curves made it unavoidable. Zwicky had been right, for decades early, about most of the universe. Since then, the evidence has only stacked. Einstein's theory says mass bends the path of light, so a great concentration of matter acts as a lens, warping and smearing the images of whatever lies behind it. Point a telescope at a massive cluster of galaxies, and you can see the warping directly. Background galaxies stretched into thin arcs, like reflections in the shoulder of a wine glass. Read the arcs, and you can map what a mass actually is. The maps agree with the rotation curves and with the two fast stars of the little dwarf galaxies we met in the local group. The mass is real. There is several times too much of it, and most of it sits where nothing shines. So what is it? Here, honesty must be total, because this is one of the largest open questions in all of science. Dark matter has been weighed, mapped, and traced through billions of years of cosmic history. We know how much there is. Of all the matter and energy the universe contains, the ordinary kind, atoms, stars, planets, comes to about 5%, and dark matter to roughly 5 times more. We know where it is. We do not know what it is. For decades, exquisitely sensitive detectors in deep mines have waited for a single dark matter particle to announce itself. So far, silence. Something makes up most of every galaxy, including the one you live in, and its nature is simply not yet known. Vera Rubin died in 2016. She had opened one of the great scientific questions of her century, and she was never awarded the Nobel Prize for it. A major new observatory in Chile now carries her name, and its task, fittingly, is to survey the dark. One more thing about that unseen scaffolding, and it is the doorway to the final line of your address. Dark matter does not merely hold galaxies together. Its gravity decides where galaxies can exist at all, and on the very largest scale, the scale where whole galaxies shrink to bright specks, the dark has a shape. Pull back now, farther than we have yet gone. Let the Milky Way shrink to a speck of light. Let the whole local group close up into a small huddle of specks. Keep going until the specks number in the millions and your view is a billion light-years wide. You might expect, at this scale, a fog of galaxies spread evenly in all directions. What the Great Galaxy Surveys actually found is one of the most arresting images in science. The method sounds almost clerical. Measure the position and distance of galaxy after galaxy. Thousands at first, then as the surveys industrialized, millions, and plot each one as a single dot in a three-dimensional map. For decades, the dots accumulated, and slowly, out of the accumulation, a picture developed like a photograph in a tray of chemicals. Galaxies are not scattered. They are strung. Across the largest maps ever made, galaxies gather into filaments, luminous threads tens or hundreds of millions of light-years long, and into sheets and walls where the threads weave together. Between the threads lie the voids, colossal rounded hollows with almost nothing in them at all. One of the largest known, the Boötes Void, is a cavity hundreds of millions of light-years across containing only a few dozen known galaxies, where thousands would be expected. A galaxy near its middle would see an almost empty sky, its nearest neighbors unreachably far. The whole arrangement looks unmistakably organic, like foam or a sponge or the branching web of a nervous system, matter in threads, emptiness in bubbles. Astronomers call it the cosmic web, and it is the largest structure there is. Nothing bigger has ever been found, because above this scale the universe finally becomes smooth. And its origin is a face you have already seen. The web is the ripples, grown up, the 1 part in 100,000 unevenness of the infant universe, pulled on by dark matter's gravity for 13 billion years, drained the voids and fattened the threads. The faint pattern frozen into the universe's first light, and the luminous web in the galaxy maps match, seed to tree. The largest structure in existence is the enlargement of the smallest wrinkles there have ever been. We know this with unusual confidence because it is one of the few claims in cosmology that can be tested by rerunning history. Give a supercomputer the infant universe, the measured ripples, the measured mix of ordinary and dark matter, and let simulated gravity work on it for a simulated 13 billion years. Out of the smoothness before your eyes, condense filaments, walls, voids, and knots of galaxies, in the same proportions and on the same scales the telescopes actually find. The web in the machine and the web in the sky match. We understand, at least in outline, how the universe got its shape. So the final lines of your address can at last be written. The local group is not alone. It is one small huddle on the outskirts of a swarm of clusters called the Virgo Supercluster. And in 2014, a team led by the astronomer Brent Tully mapped the flows of thousands of galaxies, which way each one drifts as if charting currents in an ocean, and found that our entire supercluster is itself one lobe of a vaster gravitational basin, a structure 520 million light-years across, holding the mass of 100 million billion suns, roughly 100,000 galaxies. They gave it a Hawaiian name, Laniakea, immense heaven. Everything in Laniakea, our galaxy included, is drifting gently toward a distant concentration of mass called the Great Attractor, a region frustratingly hidden behind the dust of the Milky Way's own disk, as if the one thing blocking our view of where we are going is home itself. The drift is unhurried even by cosmic standards, and the expansion of space means the basin will never fully gather. Laniakea is less a place than a current, the watershed of all the paths of all the galaxies falling loosely together. Our continent model finally gives out here, and it is worth watching it fail. Shrink the Milky Way to a continent on the Earth, and Laniakea is 20 million kilometers across. Even with the galaxy reduced to the ground beneath your feet, the last line of your address escapes the entire Earth, Moon system, and stretches millions of kilometers into interplanetary space. There is no model. Some sizes must simply be said and left standing. And with that, the address is complete. There is nothing more to write. Above Laniakea, there is only the smooth, threaded universe, the same in every direction, which leaves only one place left to go: home. Read the address backwards now, line by line, and feel each door close gently behind you. Laniakea, immense heaven, 100,000 galaxies falling loosely along the same slow current, a watershed of light 520 million light-years wide. Inside it, near one edge, the Virgo Supercluster are a swarm of clusters, and on the outskirts of that swarm, easy to overlook, a modest huddle of 50-odd galaxies bound quietly to each other while the universe stretches around them. The local group. Inside the group, two great continents of stars, closing their ancient gap at 250,000 miles an hour, unhurried, their far-off meetings still written in pencil. Andromeda and ours. Ours. The Milky Way, a barred spiral 100,000 light-years wide and 1,000 thick, a compact disk of several hundred billion suns turning once every 250,000 years, wrapped in its invisible halo, threaded with the star streams of the villages it has absorbed, still quietly absorbing one more. Inside the disk, out on a minor spur between two great arms, the Orion Arm, a side road 26,000 light-years from the center, where nothing much happens, which is a fine quality in a neighborhood. On the side road, one star among the hundreds of billions, a red blood cell on a continent. The sun, 20 laps old, mid-stride in its 21st, carrying its coin-sized family of worlds. Nothing distinguishes it from 10 billion similar stars in this one galaxy alone. Nothing except that around it, on a small warm world, there is somebody keeping track. And on the third of those worlds, in the thin layer where the rock meets the air, behind one particular window, under a lamp, you, holding the whole address at last. It took roughly 1 human century to write those lines. When your great-grandparents were children, the finest astronomers alive could not have filled in a single line past the Milky Way, and were not sure there was anything to fill in. Everything above it, the group, the supercluster, Laniakea, the web, was discovered, argued over, measured, and named inside the span of a few human lifetimes, some of it inside yours. Every line of it was earned. The milk resolved into stars by a professor in Padua. The disk mapped from the inside like a forest. The islands proven by a woman counting lighthouse rhythms at 30 cents an hour, and a red VAR on a plate of glass. The family found, the construction history read from streams of stolen stars, the dark scaffolding weighed, but not yet named, the web traced back to wrinkles 100,000th deep. A century ago, the wisest people alive could not say whether the universe held one galaxy or many. You now know your address to its final line. That is not a small thing to know. That may be the fastest any species has ever learned where it lives. And if the sky is clear tonight, the second line from the top is waiting for you. Step outside, find a faint gray thumbprint in Andromeda, and look at it for a moment. One continent of stars regarding another, across light that left before your species began. The universe is very large, and it is very old, and almost all of it is elsewhere. But of all the addresses written in it, this one, this arm, this star, this window, is yours.